All right, we're going to have our final two talks of the day. First up, we've got Parna from the University of Leeds.
Thank you, Ellen. Hi, everyone. Today I'm going to talk about how human mobility and urban structure affects cholera transmission. I'm a postdoc at University of Leeds. So what you are seeing on the right side here is probably the most famous cholera map made by John Snow, the 1854 London cholera outbreak. So what he did was traced all the infection points, traced all the taps, and figured out it's not actually airborne, it's actually waterborne. And then the government took steps sanitizing the taps and made a pub in his name, which is still there. So currently what I'm trying to do is think about more of a routine, habit, behavioral side of mobility and how that type of mobility patterns affect the transmission, and different city structures might affect transmission as well. So first I will discuss why this mobility and different mobility patterns matter for cholera. Then I'll show you the model, and then I have different scenarios or experiments that I did in the model to see how that transmission differs in different scenarios, eventually the results, and how we can use the model in the future. Cholera is generated through the exposure network, and it's not a direct network. So what I mean by that is a susceptible person might not ever meet an infected person, but might still get exposed to the disease by using the same tap or any kind of same sanitation system. So clearly it depends on where those individuals live, where they move, which schools or markets or whatever activity points and sanitation points they use, so the shared infrastructure, and how that eventually accumulates the burden, the disease burden in those specific points, and then who gets infected and where they come back with that infection, etc. So as you can tell, that this heavily depends on human movement and routine and habit, so that where this mobility behavioral model comes in. So adding mobility to cholera transmission is not a new thing. There are several studies and literatures that have shown that adding mobility might actually predict the outbreak much closer. As you can see in this two plots in one of the papers, they showed that it's much closer to the field data than when you don't add mobility in the model. Now, that's all good. So what I'm doing here is adding mobility as a behavior aware or aware of individuals' routines and movements, and not just like an aggregated flow. Because every person would have different preferences, where they would like to shop, where they would like to go for school, and that will create different patterns, and that will create different shared infrastructure and the disease burden. So when you use like a radiation model or gravity model that aggregates the whole flow, that will tell you how much trips they do, where they go, but they don't really capture those inner habits and routines. For example, if an agent wants to go to a market, it will prefer a market that it knows or have visited previously, or if it wants to explore somewhere new, it will see whatever is the closest, or whatever is the biggest, or whatever have the shops that the agent wants to go. Now, this is the overall model architecture. So first we have the city, substrate, so the city, how we build the city and the boundaries and the streets and all the points of interest, etc. Then we populate the city with agents. Agents have daily routines that they follow, and beyond their daily routine, they follow this mobility model driven by their habits and routines. Then we have the environmental layer, where they get contaminated from sanitation points, or they will contribute the cholera virus to those sanitation points, which is where the disease model comes in, which is here, it's the ACIRS model. So the environmental layer, all the mobility layer, the environmental layer, and the disease layer all combines to where the disease accumulates and for which individual. So first we built the city system. We tried to use all public data like OpenStreetMap, etc. The problem with that is the data for some cholera-affected cities are very sparse. They don't have good POI data or good admin boundary. And we wanted to build a framework that we can apply to any city in the world. And it can be like a generalizable framework. So what we did is we used only there is a very minimal output model, so you have to use only the OpenStreetMap city name tag and the center location of the city from GeoNames, and once you input that, it builds the whole city structure, and then it includes the population density of that city and uses that to find a functional boundary. As I said, admin boundary that is available for most cities are either not very accurate or too big, includes like mountains and lakes where people actually will not visit and the disease will not accumulate that much. So we used a threshold-based algorithm, which is percolation-based city clustering algorithm, to find a functional boundary. And then once we have the city, we then include the street network to see which parts of the city are well connected, more central, which then helps us identify the main hub of the city, which is the red area there, and the local hubs, which are the orange areas there. So that shows us how the city is spread. So if a city have a very dominant main hub, that means it's more monocentric. So all the activities will be there. So it will attract most of the agents there. If a city have more distributed hubs, that means it's more polycentric, so all the local hubs will have similar amounts of activities. And then we populate the city with agents and other points of interest like schools, markets, and sanitation points. So this system is quite straightforward once you have the framework down, because then you can actually replicate this for any city in the world, which is quite helpful. So as I said, the agents have daily routines that they follow. So they start from their homes or residential area. They each have their own routines. Traders goes to markets or workplaces, and students goes to school and other areas. This is all based on information based on previous literatures that have seen at like daily routines like this, or general data. And the rest of the time, agents follow a model called DEPR model, which is the main behavioral mobility model here. I'll explain that in the next couple of slides. So at night, obviously, most of the agents are inactive or not moving. And how they get contaminated is when they're moving, they have like this hydration timer and defecation timer that will run out, and they need to use the sanitation points. And then comes the disease layer of it. I hear you say CIRS model. How they get contaminated is, again, when one of those sanitation timer goes off, they need to either go drink water. If the water point is contaminated, then a susceptible person will get exposed. And all the agents, all types of agents except recovered, will contribute virus to the system, infected agents being the maximum amount, and recovered agents have waning immunity as well. So now the mobility model that I was talking about, it's called density augmented exploration and preferential return model. So the basic idea is an agent will have two decisions to make. Either it wants to explore a new location or wants to return to a previous location. So when it wants to explore a new location, it will see, as I said, which one is nearby, which one is more attractive based on size or other preferences they might have. When it returns to a previous location, it will choose from the memory that they already have. So as the model runs longer, they will have longer set of memories, and the longer the model runs, they will set into a more habitual mobility and more routine driven mobility rather than random walk. So this is the equation layer of it. First we have the exploration probability. So ST there is that memory I was talking about, is the number of unique places they visit. So once we have the set growing bigger and bigger, the exploration probability will decrease. That means the agent will set into a routine. Then we have the how they choose the new location, which is the gravity model on the top right side. It's currently based on distance in this model, but you can make it based on anything you want based on the circumstances. And the equation at the bottom, it just brings everything together of the destination choice and what you want to do. So this part here is the connection between that behavioral side I was talking about and the exposure network. Oh, sorry, not here. So now we have the model, we want to compare various different scenarios. So the main two things that we can think of that will change the mobility network is quarantine or mobility restriction. Just cut off all long-range movements, make it more local. And the next is a bit more complicated than that, which is decentralization. So instead of cutting movements, what you do is you move all the points, sanitation points, markets, schools, whatever you need in your local area, so you don't have to go to the main center and you can stay more local. So both the things in terms of like how much people are moving and how long they're traveling, both the things are kind of doing the same thing, but they will change how people interact. So that means that the exposure will be different, even though the mobility is more local in both the cases. So next, we wanted to see for the decentralization scenarios, what kind of activity points and sanitation points, how can we change them? And if we change them just the schools or just the toilets, how would that affect the transmission rather than just making a random guess and putting things in local hubs? So there are three types I checked here. First, the POI decentralization, which means I move only schools, markets, and general POIs where agents might visit. Then I have the WASH decentralization, which is the sanitation points, and then I have a combined scenario. So the bottom two heat maps basically is showing that when I do all those decentralizations, it actually makes things more local. So that's just a model check that it's not doing something unusual in there. So first, I want to see, did that actually change the mobility? Did that reduce the exposure? And where the risk is, and how can you basically explain that? Because as I said, I don't just want to reduce the epidemic curve, I also want to see where I might have to apply sanitation or apply vaccination, etc. So first I'm checking if that all those scenarios are changing the mobility pattern. So what I checked here is the completed visits per agent per day, and how the visits per used facility is changing. So as you can see, the baseline, it changes at a great deal from the baseline scenario, and obviously generic POI and the WASH facilities have the most amount of changes. So that's the overall mobility. It doesn't look at anything local or nearby, which is what the next one does. So here I'm checking that if there is a market or a school or anything nearby a sanitation facility, does that sanitation facility get more visits? Or does it depend on the geography, or does it depend on solely where the agents are traveling? So what we found out is it doesn't depend on just proximity. It also depends on access. So a tab can be spatially closed, but it might not be that important, or it might not where the disease accumulates. So these are, sorry. So these are all the findings that the decentralization is showing what we thought it might. Now we also checked the total burden. So the cumulative exposure is the lowest for when we do the combined decentralization, which is actually we also see here. So this is where we see that for all the cases, any POI visit followed by a TAP visit within the 6 hours, and the colors show that how many days it takes for the first infection to arise, and the combined case have the longest duration. So that means that that might be the best case scenario. Which is what we see here. So cumulative exposure and the peak burden is actually the lowest for that combined scenario. So the strongest, so it actually means that it's reducing the pressure on all the points, which is eventually reducing the epidemic burden in total. Now, sanitation is important for cholera is not a new result. We all know that. So what I'm interested here is, now that we know that our model works in a way that we want it to work, can we see where we have to focus, which points it might need extra special care? That's where the spatial hotspot comes in. So these are all the 4 scenarios, and as you can see, for the baseline scenario, the hotspots are concentrated around the main hub. For POI, there's a little bit on the secondary hubs, but for the last 2 cases where we moved the sanitation around locally, and the hotspots are much more spread out, much more around the secondary hubs as well. So this means that decentralization might or might not reduce epidemic burden, but it definitely does change where you can see the hotspots. That might mean now that if we, for example, in the last combined case, if we zoom in on that secondary hub, we will be able to figure out what tap is actually the source of the infection there, or what mechanism, not just taps, what mechanism do we need a mobility restriction just in that hub for the whole city to reduce burden, or do we need to sanitize just that hub? So it basically reduces cost and time through targeted intervention, which is what we wanted to see here. Now, back again at including the quarantine. So quarantine here, intervention B is quarantine and D is the combined decentralization. Forgot to change those names from my code. So quarantine here acts as the best intervention, both in epidemic burden and spatially. Does that mean that we should forget or everything that I just discussed and just quarantine everyone? That might not be the best case scenario for certain cities. We might have to think more about it. And maybe if a city is cholera affected every year, we might have to think about decentralization as a intervention rather than quarantine every year. So we are currently looking at various strengths of the quarantine and how that affects the disease burden. So this is just a preliminary result. Now, what we got from all of these results is basically you don't need to think about the whole city as a uniform matter and apply, for example, mass vaccination or mass sanitation. You can save your money and time. When there is a epidemic, if you can predict those hotspots and save your money and time, and actually might be useful, might be better. So what that's the model currently, but what can this model do beyond that? I think the broader implication here is the framework that is aware of the individual routines and habits. And what's interesting there is you can actually include more behavioral aspects of it, which actually we're trying to do. We're trying to understand why the agents do certain things or go certain places, what's the motivation behind it, which will be quite interesting to see. And then eventually, once you have all those factors, you can build kind of like a, I don't want to actually use the term so lightly, but like a digital twin of a city, and you can predict the disease, the burden, and the hotspots before any epidemic, and focus your attention there. So obviously there are limitations. The main limitation is the limited data, detailed mobility data, which is very important to validate the model. We obviously have validated the mobility and the city structure on data that is available, but they are not cholera affected cities, so it will be great to have data from those areas. And as the city representation is a proxy, so but you can easily change that. You can bring in data and validate that part of the model to make it more realistic. So currently we are actually seeing how we can see multi-city simulation. So we are interested in, for example, if two cities from the same country behave similarly, and if we can make a decision that cities in that country will need the same type of intervention, or if two cities of similar structure behave similarly, etc. So we are doing a multi-city simulation. We currently have like 50 different cities from 10 different countries. And also, as I said, understanding the reason behind those movement behaviors would also be our next step in this model. Yeah, and thank you. That's all. Any questions or comments or opinions about the model, please? Thank you.